So previously we discussed geometric ways of thinking of least squares and how we can develop some intuition geometrically. So least squares also has an insightful probabilistic interpretation that we can also use to analyze its properties. So in this part of the course, I want to discuss the probabilistic interpretation of least squares, which can help us think about our model. It can help us think about what kind of assumptions we're making with our model and whether those assumptions are reasonable, and also develop even more intuitions about what it is that we're doing and what our model is assuming. So let's recall from previously the Gaussian distribution, multivariate Gaussian in n dimensions. So assuming that the covariance matrix is diagonal, so we write the covariance as this variance sigma squared times an identity matrix. We can write an n-dimensional Gaussian in this way, where we take the dot product of the output of the random variable y minus its mean mu, and then the dot product of that, and pass it through this density function. So now let's ask, what happens if we put a restriction on the mean of this n-dimensional multivariate Gaussian? What if we define the mean vector mu to be equal to the matrix X, which we form by taking our inputs and putting them along the rows of the matrix as usual, times a vector W, which is something that we don't know. So X we know, W we don't know, and we want to learn it. And we're now going to say that mu is restricted to have this form. So we plug this matrix vector product into the Gaussian for mu, and then we say, let's find the maximum likelihood solution to W. So let's find, in other words, the value of W that maximizes the log likelihood of the output vector y given a mean that has this form and given a covariance that has a diagonal covariance where each dimension has variance sigma squared. So when we do this, when we take this multivariate Gaussian and take its log, we get this function. And now our goal is to find the vector W that maximizes this function, which is the vector that maximizes the likelihood of the data outputs y that we see given the corresponding inputs x. And so immediately we can see that least squares and maximum likelihood in this case share exactly the same solution. So remember, what's the least squares problem? We want to find the vector W that minimizes the sum of squared errors. What's the maximum likelihood problem for our n-dimensional multivariate Gaussian assumption on the data? We're trying to find the vector W that maximizes, so previously minimizes, now maximizes the log of the likelihood of the data over W. Because this term here does not involve W, we don't even bother to write it. And so we're trying to find the vector W that maximizes this function. What you notice is the negative sum of squared errors times some scalar. So this scalar doesn't do anything. So it should be clear that these two problems share exactly the same solution. This is essentially the negative of this problem, but because here we're trying to minimize and here we're trying to maximize, they have exactly the same solution. So therefore, in a sense, what we can think of least squares as doing is making an independent Gaussian noise assumption on the error. So this is it's just some intuition that we can develop where we say that the least square solution corresponds to the maximum likelihood solution of this multivariate Gaussian assumption on our data. And so it's like saying that each of the errors are independent and identically distributed as a zero mean Gaussian with some variance sigma squared. And so we can say that we're effectively modeling our output as being equal to the dot product of the input with the weight vector W plus this IID Gaussian noise. Another way we can say this is that we're modeling our outputs as independent Gaussian random variables, where the mean is equal to the dot product between the input xi and the coefficient vector W, and the variance is sigma squared for each of the observations. Or, as on the previous slide, we can simply say that we're making an assumption that the vector y is a multivariate Gaussian with mean equal to x times W, where this x is formed by putting each observation input on the row, and covariance equal to sigma squared times I, so a diagonal covariance. So this is like an assumption that we're going to make. We're going to say that our noise is IID Gaussian, essentially, and that maximum likelihood for this modeling assumption is the least squares solution. But using this additional probabilistic line of analysis, we can better understand the maximum likelihood solution and therefore the least squares solution. Okay, so let's look at some of the things that we can say if we make this modeling assumption. So again, we're given the modeling assumption that our observations y, so the outputs that we observe in our data set, were generated according to a Gaussian with mean equal to xw, and then IID noise, Gaussian noise. So this is going to be the modeling assumption that we make for how we observed the data, how we obtain the data y, given the corresponding inputs x. So first let's ask, what is the expected value of the maximum likelihood solution? And when I say maximum likelihood, you should also think least squares solution because they're the same. So what is the expected value of the maximum likelihood solution under this distribution? So what we're saying is, what is the expected value of WML? We know that the maximum likelihood solution is equal to this. So we have this matrix product. There's nothing random there. But then we also have the output, the observation vector y, and we're making a distribution assumption on how y is generated. So y is random. So really, we can write this term like this, where we have the function times the distribution of y, and now we're integrating over y. This is the expectation function. So, of course, every expectation you have some assumption of the distribution that you're taking, some distribution you're taking that expectation over. In this case, it's the distribution on y. So we have a function of y times the distribution on y, the density of y, and now we integrate over y, and that gives us the expected value of this function of the data y. So by basic manipulations of the expectation function, one rule is that because this term here does not involve y at all, it's a constant, there's nothing random here, we can bring this outside of the expectation and obtain this. So really, we want to take the expectation of y. And because y is a multivariate Gaussian with this mean and this covariance, we know the expectation is just equal to whatever the mean is. So we plug in the mean, which is x times w. Again, we don't know w, but we're making an assumption that there exists some w. And so therefore, the data has this mean where the truth, the ground truth of what w is plugged in order to generate the data. So we input, we replace the expectation of y with its mean, even though we don't necessarily have a value for w. And then we find that here we have x transpose x. Here we have x transpose x inverse. That matrix product cancels out, and we have y. So what this is saying intuitively is that if we have some ground truth value for y, or for w, And we have some inputs x that we construct in a matrix in this way. And then we generate an output y according to this distribution. And then using that output y, we solve the maximum likelihood solution for w. So we have the true w, and then we, using the random vector y, solve the maximum likelihood solution for w. The expectation of our maximum likelihood solution is equal to the truth. In this case, what we're saying is that the maximum likelihood solution for the vector w is an unbiased estimate of the ground truth vector w, which we don't have access to. So this is good. Least squares or maximum likelihood for this model is going to, in expectation, give us the true parameter, which is what we're trying to learn.